Good morning, everyone. It's a great pleasure to welcome you all to this Dumatec webinar, which is the last of a series of 4. My name is Charlotte Israelsen, and I'm the Global Key Account and Market Manager responsible for the Global Laboratory segment. If you missed our previous webinars on the Keltec, Soxtec, and Fibertech solutions, you do not need to stress, as we have recorded all these webinars, so please feel free to reach out to Marcy Russell, who will be glad to send you a link to the webinars. Please note that today we have a campaign prize for the Dumatec. You can also reach out to Marcy and she will tell you more about the prize. As a laboratory, it's critical to maintain analytical instruments in order to ensure accuracy and decrease downtime. The main focus on the webinars will therefore be describing theory, basic maintenance, and troubleshooting of our automated chemical solutions. Today we will cover FOSS fully automated solution on the Dumasın method, the Dumatec. But before we start the webinar, I would like to highlight some housekeeping items. If you cannot hear the introduction at this time, please check the volume of your computer. All line must be muted during the presentation. Use the key function during the webinar to ask your questions. The line will be open again after the presentation. All questions will be compliant and answered. The key presenters today will be Carrie Sun, who is our product manager, and Jacob Everson, who is our product specialist. Jacob will introduce you to the product theory, including application for the Dumasın. Hereafter, you will be trained in basic maintenance of the Dumatec, including connectivity. Carrie will also show you some videos. Hereafter, Carrie will teach you about troubleshooting for the Dumasın method. Bradley Buckman, who is our Field Service Manager in North America, will give you a short introduction to our service organization. And finally, but not least, Marcy Russell will give you an introduction on how to contact your local sales organization. We appreciate very much that you consider spending time with us today. And as a big finale, we have a special prize campaign on the Dumatec. To learn more about this special offering, please contact Marcy Russell. I will now hand over the word to Jacob.
Hello, my name is Jacob. I'm a product specialist at FOSS for the lab segment. And thank you, Charlotte, for introducing the Dumatec for this webinar. I'll go through some slides about theory for the Dumatec and application, what kind of application nodes we have at FOSS, and it will take about 20 minutes. And after I've done my presentation, Carol will talk about connectivity and maintenance and troubleshooting, and then we'll have a Q&A session at the end of this webinar. So the Dumatec is an instrument that in just 3 minutes do a protein analysis, where you measure on a gas. The nitrogen, element of nitrogen will be measured in this instrument. So it has a 3-minute runtime if it's a started up instrument, and you have low running cost and reduced workflow in this instrument if you compare it to another other way of measuring proteins. And the Dumatec is using a Dumas combustion method, and it was a French scientist, Jean-Baptiste, in the 1800s that made this invention, and the first real instruments became available in the market in the 1970s, and now they call it Dumas nitrogen analyzers. So the Dumatec and the Dumas method is using a combustion principle where the sample is combusted with oxygen, and a helium is used, or you can also use argon in some cases, for transporting the combustion gases, and that's primarily water, CO2, and different kind of NOx gases. And then they will be filtered through various filters and traps, and finally go to a thermal conductivity detector and be measured. So you have a signal. The reaction here is that you have a sample, you have oxygen, it will combust into these gases, CO2, water, and other oxide, NOx, and they will be further reduced. This is the reduction column that is containing copper into these gases, and in the end you have elemental nitrogen that is measured by the TTC detector. And then you do a calibration curve, and on the basis of that the unknown sample can be measured also. There will be more later in the slide. So the principle and diagram is displayed here. You have the autosampler here. That is the same you see here. And we have an option of, this is just one disk that contains 40 samples, and you can have 3 disks of this. So that's 117 samples, because you need to have the hole going through into this combustion reaction. And here, this is the crucible that contains the sample that will drop down here, and the oxygen and helium is supplied to this, and then the gases will be the sample will be combusted here, and the gases will be released at around 1000 degrees. All the gases will be then transferred through the combustion reaction, going in here and to the reduction column that contains copper. So that will reduce the NOx going through the system. And then there's a water trap here, the F1, that will remove some water. The F2 will also remove water. And also the F3 is a water trap. There's different kind of water traps. I'll come back to that later. And then finally here, there's CO2 traps that will catch the CO2. And this is a carousel consisting of 6 CO2 traps. They will be regenerated on a regular basis. And then finally, the elemental nitrogen will go up here to the TTC detector. And you have a spike. The more nitrogen, the higher the peak and peak area. And then the peak area will be integrated, and on the basis of the peak area, you can do a calibration curve. So, and that will be all collected in a PC that is having this software installed for the Dumatec. And this is the autosampler and the personal computer, the connectivity detector, combustion reaction, and so on. So this is the principle, all combined in this instrument. And here, more overview of the instrument. Again, the reduction column, the combustion reaction and the reduction here. And in the software, there's some consumables that are needed to be replaced on a regular basis. It depends on the usage. And in this, you have the lifetime. This is the factory default lifetime. But of course, it depends on the usage, that what type of sample is running and how much sample amount is putting into the crucible. So the crucible is set at 120 samples, but it can, if it's a lot of samples with absorbent for liquid samples, then the 120 may be a little bit much, then maybe 80 could be what is within the crucible. It's important not to overfill the crucible, so when you can set limits for this, so you don't have the crucible be filled up and sticking to the walls. So it's important to avoid this. But as mentioned before, the sample will drop down here, be combusted, and then the gas flow is like this, going through the different systems. The water trap here is a condenser. This is the F2, this is a permeable. And the F3 is a silica gel that is need to be replaced. And a little bit more of the operation procedure and how the gas is purified. F1 is a condenser. The F2 is a permapure, and it will last 2 years. It will go from white to black color when it's used. And this one is a silica gel that removes the remaining of the water. And actually, This is the F3. When the silica gel is going from orange, when it's fresh, to a white pale, then you need to exchange this. And the F2 is a permapure, where the water molecules can permeate this this tubing, and then hence make sure that the nitrogen will continue in the tube, but the water is separated in this permapure. So the principle is that the TDC signal here will increase as on the basis of the amount of nitrogen reaching the detector, and on the basis of this you can create a calibration curve where you know the amount of nitrogen introduced into the system, and there's a description in the user manual how to do the calibration curve, and on the basis of the calibration curve you can insert your unknown sample and then go over and have a reading that, okay, this is the amount of nitrogen that is in the sample. This is just some principles of the Dumatec and the calculation of the nitrogen, and then you do add the protein factor to convert it into protein. And here there is a picture of the crucible, and this is can consist of 120 samples if it's solid samples and not so much weight into the tin foils, but if it's liquid samples where you have the sorbent, then the lifetime can be adjusted. You can set all these warnings can be set in the software depending on the usage. So it takes a little bit of running some samples before you know what type of real lifetime is for this. The copper wires, you can have copper powder, and there's a copper wire. The copper powder is more, the surface area is bigger, so the lifetime is depends on but around 400. So, and also the silica gel. You visually can see the silica gel is, if it's pale, and then it doesn't work. And you can see it also in the plot and the integration that the water is popping up. Then you need to regenerate this silica gel. So now go to some Dumatec applications, just some theory. For measuring protein, the Kjeldahl method was invented in 1883, and then Dumas as a running method was done in the 1980s, and it's a combustion method. This is a chemical method, and the FCR method is also from the 80s. So there are different ways of measuring protein or nitrogen. And Dumas method is also official standards for these ISO and AOSE methods. I'm going to go through a couple of these. So this is an example of ISO standard for the Dumas measurement of oil seed and animal feed stuff and cereals, and the AOSE methods for meat and cereal grains. So it's an accepted method for measuring different kind of samples. Here is more examples for the sample types is listed here, and you can have a look. There's a lot of variety, and the AOSE methods or ISO standards listed here. An important thing for the Dumas method is that when the sample version needs to be a representative of the bulk. So the sample size for the Dumas is very small, so it's important that the sample is homogeneous, and also that there's no atmospheric air in the sample, because this will interfere with the results, as the atmospheric air contains nitrogen. So this is avoided by wrapping the samples in tinfoil cups, and the air is pushed out with a special tool. And solid samples, they can be grinded. And this is the FOSS sample mills, the Simutec, the cyclotech and the knife tech. So you can have it's important to have a homogeneous sample. And the particle size should be less than 0.5 millimeters. And liquid and semi-liquid samples is captured in an absorbent for liquid samples. It's included in the, if you buy Dumatec, and you can buy it as a consumable also. But this contains like an ash without, there's no nitrogen in this, and it will absorb the liquid so it can be packed within the tin foil and wrapped. And the samples are analyzed within an instrument. There's the default method A, B, and C. And Carol will talk a little more what these methods, how they, what the programs are for this, and which samples to use for these methods. But it's in the software. I will also go through an example later. So the sample size, you need to, it should be between 80 and 200 milligrams. If you're above 200 milligrams, it can be difficult the tin foil will be overfilled, and 80, it's maybe too less to get a good signal for the TDC detector. That depends on the protein content, of course, of the sample. But the less you can have signal, the more you can have in the crucible. So it needs there's a variation. The balancer is used for weighing the sample, must be within at least presence of 0.1 milligrams or better. If you can have 0.01, it's for weighing. If you weigh less small sample amounts, it's better. It's called analytical weight. Calibration curve. This is done. You need to do a calibration curve before the sample is introduced. I'll go through an example later. If you know the sample, then the calibration, the sample type should be within the calibration range, of course. And as a standard, the EDTA is supplied for the Dumatec, and it's for most instruments in the industry. This EDTA can be used for standard, where we know this content of the nitrogen in this compound. So the general application node is this number here, AN0330, and it's called determination of nitrogen according to Dumasın method. And this is the peak area, and on the basis of the peak area that is detected by the detector, you go in and measure the protein or the nitrogen content, and then you apply the protein factor for the sample types. It can vary, so you need to look up in the standards what the protein factor to apply this. Here is the calculation formula for this sample protein nitrogen content. And verify samples, when you've done the calibration, verify samples can be inserted as a control sample, where the nitrogen for the EDTA should be within this range, and if it's not within the range, when running a verify sample, the instrument will stop and say it's out of spec. You can also set it as an unknown sample and still have this quality control, and then the instrument will not stop. So this is just an example of a preparation of a calibration curve, which is needed before running real samples. So this is both TRIS and TAM and EDTA calibration curve. It's for low proteins. So this is the formula for the EDTA, the normal supplied standard, and this is TRIS TAM. This is the chemical formula. So this is a solution, and the EDTA is a solid powder. So you need to have some pipettes to do the standards for the solution, and the EDTA you can just weigh it in using this spatula. And on the left here, this is the Dumatec sorbent for liquid samples. This is needed when you do the standards for this TAM and TRIS solution. The special tool is here, where you form the tin foil so it can stand on the balance that is here, and then you weigh in your sample directly into the balance, and you will get a reading from the sample. And actually, you can connect a sample directly to the Dumatec software, so the weight will be transferred into the sample table using this connection. Yeah. This is how it looks like for the calibration curve. Standards are listed here in the software, the EDTA and the tris and tau, and the nitrogen content is listed here. So this is the calibration, an example of how to do a calibration curve, where the blanks are running first, and you need to have a blank. And when you do a new calibration in the software, you select new calibration, then the software knows now it's going to make a new calibration. And the first one should be a bypass, where there shouldn't be a very low signal for this bypass. And then you have the same standards coming here. The method A is for solids, EDTA, and method C is generally for liquid samples. So all of these is the liquid samples, and here this is the solid samples using the EDTA. How to prepare the tris and tau solution? For example, standard 1 is 10 micrograms of sorbent and 10 microliters of standard. It is important to have this low baseline as the lowest signal you can see from this standard, so there's no interference for the signal. This is the online plot that you can see in the instruments. So this is the calibration curve that is being produced. This is the software, and here this is the calibration. And all this should be within the 0.999 for the regression. And this will result in a calibration curve from 0.1 to 50 milligrams of protein if this factor is used. And this is some test for running this calibration. This is oat solid, and all this is liquid samples. Strawberry banana smoothie, infant formulas, oat drink, and rose hip apple soup. And on this is the verify samples. This is bracketing the samples. So this is a control of if this is passed and this is passed, then you know the instrument is within the range. This is the online plots for the oat. This is high signal, and this is all the low protein samples. And this is the bypass signal that should be giving a very low signal. The Dumatec software will create a report that you can export to Excel. It will make all this from date to protein, but not the statistics that you can do yourself. And this was an example. You can see also the verify samples here and here, and they are within this range. So this run is okay. This was just some a brief introduction to the Dumatec theory and what application we have. And at FOSS, you can go in and have a look at the service toolbox. This is the application that we have for the Dumatec so far. This is what we are planning to do and calibrations on. And if you have any questions or thoughts about the Dumatec, please contact us for the global support. And now Kerry will go over and take over from connectivity and maintenance of the Dumatec and also some troubleshooting. Thank you.
Thanks, Jakob. My name is Kerry Sun. I'm product manager in FOSS for the CA instrument. Today, I will just introduce you a few things about Dumatec. First, I will start with the FOSS Manager. It's a tool used to monitor the Dumatec result data and error message. Also, this is a tool used for monitor other FOSS near instruments, the result and also other informations. So the Dumatec instrument can upload sample data, and error code to the FOSS manager. And this is possible via extra FOSS data uploader application installed on the Dumatec instrument PC. And this uploader is called GIDU, G-I-D-U. And the data from connected instrument is automatically uploaded to the FOSS manager server, and from here, data available for one or more FOSS manager users. So the users can review the data or the error message from FOSS manager server, as shown in this picture. And here's a few benefits for the FOSS manager for the Dumatec. So the instrument have higher availability for sample analysis, since all the inspection, reporting, export of normal and the quality insurance sample can be done from office by FOSS manager client. And also the lab manager and the QA personnel can save time because they don't need to just go approach the instrument, and they can check the instrument result remotely. And also instrument and the FOSS manager user can be at any location, so one person can monitor several instruments at different sites. And the data is uploaded to FOSS manager shortly after analysis, so which means it's possible to discover problem in advance. And last, the FOSS manager database holds all the upload data. If the instrument PC is lost, the uploaded some data or the error code, and all this information is still available in the FOSS manager server, so people still can find out the data, the details. And I will show you demos of this FOSS manager client. Okay, so this is the interface for the FOSS manager client. And here you see I have a network. This network is called the FOSS Application Lab. So this is all the instruments we have in FOSS Application Lab in Denmark. And we have a few instruments like Dumatec, FullScan, MilkScan FC2, UnoFOSS, and the OneScan. And I just want to show you one instrument, this Dumatec. And so for this is like the interface, and there's a few tabs which you can check the different functions. And like for the product, they are mostly for the like it has information for what products you have, like for the method which you use in the Dumatec, like from A1 method, that means A1 method stands for the samples. And also there's other information like application model that is mainly for the near instruments. And if you want to check the instrument, the data and error code from the Dumatec, you just go to surveillance. This is the easy way, and you choose instruments you want to check. And because the synchronization already has done it automatically, if you just choose the GIDU uploader. So if you want to check what the batches you have run for the instrument, you just go to the batch and you just select the data you have, or how many days you want to check it for the period, and you do the filter. Then it shows all the batches you have run for this instrument. So this is all the batches I have run for the Dumatec instrument in the FOSS Application Lab. So this is all the batch information. And if I want to check the detail for the sample results, I just choose the samples, and you do the same for the filter, the dates, press filter, and you can get results for all the samples you have analyzed for the period, and you can get results. And if you want to export the result, it's also very simple, just to choose result with the mouse. And if you want to choose couple, you just press the control, and you can select multiples, and you just export. Then you can choose different files, the export file type from XML spreadsheet, Excel spreadsheet, and CSV file. Then you can get the result. That's very simple. So you can get the template. It's like building template. You can get result for that one. And if you want to review the error code or the messages, and you just go to the event and just filter the date, you can get all the error code or warning code in the period. So this is like there's code number, like the peak not detector is 93, And if you have some other issues like absorbent incorrect positions, you will get another error code 51. This is error absorber carousel is in illegal position. So you can just see all the problems. And also by searching the result, you can just get a pre-warning, if you have any problem for the result. So this is a normal way you can check you can do with the Dumatec FOSS Manager client. Just check the results and remotely, and also you can get a warning message in advance just to check if the instrument has any problems. Now we go back to the part for the maintenance. Here are a few maintenance information I want to share with you. So we start with maintenance that you have to change for the consumables. So this is a maintenance list that you have to change or you have to do for the instrument. It's including change crucible, or we say it's ash insert, or you change the combustion reactor, change the reduction reactor, change the CO2 trap, and change the water trap. After this is very basic, the procedures you have to do for the maintenance. And also if you change all these things, all these consumables in the daily operation, you always have to run the leak test to ensure there's no leakage for the instrument. And here is a table. It gives you this rough information, how many runs lifetime you can get for each consumables. And like, for example, the crucible, the lifetime is 120, but this is just a reference because lifetime is also depends on the sample type you are running. For example, the crucible, if you are running high ash content sample, the lifetime will be shorter. Or if you are running liquid sample because you use absorbent to just trap liquid, absorbent is part of the inorganic material. It's like an ash, cannot be burnt, so it's just a short lifetime for the crucible. And also there's another consumable that is PermaPure. The PermaPure has a lifetime like 2 years. It's maintenance free, so you don't need to change it frequently, but just this is also part of the maintenance. And for the maintenance information, the lifetimes of consumables, this is indicative. So you can see all the lifetime information from the software interface for the maintenance. And the software just automatically counts how many runs you have done since last maintenance. So there'll be numbers showing here, so how many runs. And you can define when software give you the warning message. Like here, if you set 10, that means when the 10 runs left for 800 analysis, then the software gives you the warning message that is time you have to change consumables. So that is very easy for the operator know when it's a time you have to change the consumables. So here is a list for the major consumables you have to change in the daily operations. And for the consumables, we use a copper powder that in the reduction reactor, which has longer time than other competitor use copper chips. And also in the silicon gel, we use different, for the silicon gel, use a water trap that is different from some competitors. They use they use magnesium perchlorate that is very highly flammable, and we use silicon gel that is very indication for the water. If there's moisture inside, the color change, so it's easier to tell if it's a time to change the water trap. Also, as mentioned before, the PermaPure is maintenance free, so it's easy. It's quite efficient to remove the moisture in this memory system. And also it's maintenance free, so you don't need to pay much attention to this one. It's like when the 2 years lifetime is closed, you just change it. And now I just replay the videos so you will see the detailed information how the consumables can be changed for this instrument in the daily operations. Yeah, so when we finish playing the video, here we go to the next part, the troubleshooting. I will just give you a few information what you can do with the troubleshooting for this instrument. First, with the leak test. And for the leak test, we have two different scenarios for the leak test. This is like screenshot, which from software, we have two leak tests. One is called the leak test with flow controller. The other is called the leak test under pressure. And first, I will start with the leak test with a flow controller. So the leak test with flow controller, it compares the gas flow between the flow controller 1 and the flow controller 2. So there is the gas flow is regulated by the flow controller 1 and pass through the system. And the flow controller 2 then measures the gas flow passing through the flow controller 2 and compare the value. If the value is the difference between flow controller 1 and the flow controller 2 is smaller, if it's less than 5 milliliter per minute, then the instrument thinks that then the leak is fine, there's no leak, or the leak is fine, then it passes. But if the difference between FC1 and FC2 is larger than 0.5 milliliter per minute, then the instrument thinks there's leakage. So there'll be some action to just solve this leakage. And then there's another way to test the leakage under pressure. And this is a different way to test the system. So the system is like somehow is closed from outlet, and then the flow is still going inside and build up a pressure inside the flow system. Then the inlet is also closed for the system. So now the system is complete closed system, but the pressure is building up at a certain value, like over 1400 millibar. And then the pressure inside system is just to measure the pressure, to monitor if the pressure drops. If the pressure drops, that means there's leakage. But if the pressure is stable, then there's no leakage. So if the pressure drop is slow, it's a slow rate, less than 5 millibar per minute, then the system passes the leak test. But if the pressure drop is over 5 millibar per minute, then it means there's leakage. So you have to take some action just to solve the leakage. And please note, if you run the leak test, please ensure the temperature or the flow is stable in the system. So you can either do the test when the instrument is turned on, there's no temperature at room temperature, there's no temperature change, or when the temperature reaches the setting, like at standby or the working mode. So do not run the leak test when the temperature is increasing. And also it's recommended to replace one, because every time when you replace the consumable, you have to run the leak test. So when you change the consumables, every time when you change one, you just run a leak test. Then this can prevent problems, because if you are changing too many consumables inside, then you don't know which consumables causing this leak problems. So it's very important that every time you change one consumable, just run the leak test. Then it's easier to exclude the leak from the consumables. And also we provide a very useful tool. It's called leak detector, helium leak detector. This is part number, and you can order this part number, and you can just measure the leakage from system, as you already see this in the video just played. And here is some information that's where you can check the leakage. You can expect the leakage from. So here is some pictures you can check where the leakage usually come from. This is all the positions that you change the consumables. This is the top of the two reactors, combustion reactor, reduction reactor. This is the bottom of the combustion reactor and the reduction reactor. This is the water trap 3, the silicon gel, the two ends, because you have to take out this water trap and refill it and put it back. So it has risk there be leakage at these two positions. Then also like the CO2 trap, two ends of the CO2 trap, because we have 6, and if you replace any of them, then you have the risk there's leaking from 2 ends. And also it's important that you have to check the leakage for each CO2 trap. You rotate the carousel and then you just measure the leak for each CO2 trap. So check if there is leakage in all 6 positions of the CO2 trap or if it's only one position. The leak in one position. The leakage in one position, that means CO2 absorber has leakage. If leakage in all 6 positions, then CO2 trap are working fine. So there's leakages from other positions. And also you can check if all the seals are in place. If yes, please check the lifetime of these seals. PM is may required. And because we have a few seals, they were in the auto exemplar, they are at the bottom for the bottom connection. If they are used for a time period that gets hotter, so it cannot seal the system. You have to perform the PM, preventative maintenance. Also, you have to tighten all the screws, especially the screw that adjust last time. So here is a few information for the screw, just as already mentioned. And then other common problem you see is bypass. So the first warning or error message you see about bypass is bypass not detected. This is because usually the bypass value is very close to 0, then you will get a message peak not detected. This is not a real problem because usually it happens with very good quality helium oxygen. It's very pure. So when you run this bypass this blank, you cannot see any peak of the nitrogen. So it's not a big problem. And also you will see another problem that is bypass that is too high. Then you have a real problem that you have to figure out. And usually we define the bypass or the blank should be less than 100. And if you see the value, if you see the integration of the bypass, the peak is over 100, then you have a problem. And the first thing you have to check if the plastic lid of the auto-exemplar is on. Because if you forget to put the plastic on the auto-exemplar, you will have the oxygen and the nitrogen, the air get inside into the auto-exemplar, and the nitrogen inside the air will cause high blank result. Usually it's over 10,000. And also the blank result can be caused by the CO2. That is because you haven't done the gassing, and the CO2 just released in the bypass running. It gives the signal. So you have to take around 2 hours to complete the gassing for all the CO2 traps. And the other thing also can be moisture. Moisture also can give you some high blanks. So that means you should check all lifetime for the water trap, especially like silicon gel. It's easier to tell, so you have to replace it. And the other thing is that you also the moisture from the combustion reactor or reduction reactor for the new one, it can give some high result. So note it's recommended to heat the combustion reactor or reduction reactor for 10 minutes with the top screw, the top end is open. Then the moisture can be released from 2 column. Then you also can just solve the problem with some moisture in the bypass, causing high bypass value. Then we go to the part for the sample preparation. And usually we say for decimal places, balance is fine for the weighing, and or you can choose better 5 digits or 6 digits. And also when you do the preparation, it's important that you have homogenized sample. And it's very important you get homogenized sample. If it's not homogenized, you cannot get very accurate or stable result. And the other thing here is a few requirements for handling the solid sample. You must have the particle size is less than 0.5 milliliter. This is different from shadow method. For the catalog, you should have the particle size less than 1 milliliter. That's fine, but for the Duma, you should have particle size less than 0.5 milliliter. And also the weight information. For the system we have for the Dumatec here, you should have the weight between 80 to 200 milligrams. That is used for most sample types. And for the liquid sample, and we provide absorbent that is used to trap the liquid sample in the tin foil. And this can prevent leakage of the liquid during the analysis. And we have the recommendation for the ratio between the absorbent and liquid sample that is 1:2. So for example, if you have 200 liquid sample, you must weigh 100 milligram absorbent in the tin foil. So the way you do the weighing is that add the absorbent in the tin foil first, then you just you weigh the liquid sample. So the tin foil can absorb the absorbent in the tin foil can absorb the liquid sample. And also, it's when you do these procedures, so the liquid cannot. You also, if you do these procedures, also ensure you have the right ratio, you have the right amount for the absorbent that is enough. Otherwise, you have the risk the liquid will move in the tin foil, and you will get the liquid out, or sometimes you get the weighing is not stable. And the other thing is that you should do not pack the tin foil too tight. Because usually when you pack the tin foil, you just close it and press it with some tools or with your hands, with finger. But if you are pressing too much, you will get the liquid sample just flow out from the tin foil. So just do not pack it too much. And also, if you handle the semi-solid sample like cream or the yogurt, and we have different recommendations for the ratio between the absorbent and the sample. It's 1:1. So you have 100 milligram cream, then you have 100 milligram absorbent. And then you have different weighing for the different procedures of weighing. Because here you have because for liquid sample, you just weigh the absorbent and you add the liquid. Then the liquid is absorbed by the absorbent. But when you handle the semi-solid samples, you just weigh half of the solvent at the bottom, then you add sample, then you cover the sample. With absorbent finally. So then the sample is like the sandwich is in between. This can prevent the move of the sample out of any problems. And it's the same as you should not pack the tin foil too much. Otherwise, the sample will just flow out from the tin foil. Here are some information about the method used in the Dumatec combustion. So this is method table that you can find in the software. And you see we provide different methods. It starts from A1, A1.2, B, B0.5, B1, B1.2, even you have C, C1, C1.2. And each method stands for different meanings for the oxygen dosing and the flow. So first start with the letters A, B, C. A, B, C, they have different meanings for the oxygen flow. So A means 400 milliliter per minute oxygen flow. This is usually used for the pure homogenized powder samples. And B means 300 milliliter per minute flow that is used for the mixed soil samples. And also we have C is 200 milliliter per minute that is used for liquid samples or sample hard to burn. Just have slow burn procedure. And then the numbers here stand for the oxygen factor. This is the amount of oxygen used for the sample analysis. And this number means the ratio between the volume of oxygen and the sample size. So for example, if you use 1.4, that means 1 milligram sample will burn 1.4 milliliter of milliliter oxygen gas. And if you have a sample contain high fat or high carbohydrate, that requires more oxygen. So you have to choose higher factor for the oxygen factor. And we usually have a recommendation that is B1.4. This is usually used for the universal sample types in the combustion. So you use the flow is 300 milliliter per minute, and you have 1.4 factor for the combustion. You use like 1 milligram. That's burn. If you have 100 milligram sample, you burn 140 milliliter oxygen gas in the procedure. And then we have the way how you can do optimized method for the samples. And this is the start with the take turns to run samples and the bypass. So this is the way you can run. You always start with high oxygen amount. Here example, you start with high oxygen amount B1.8, then you run a bypass. Then you start with B1.4, just to reduce oxygen amount, then you run a bypass, and even reduce 1 to 1.2, run a bypass, and then to 1.0. And you should observe the bypass. And if the bypass is higher than the previous one, then the previous method is the best for the samples. Because if the bypass is higher, that means there's like a carryover in the system. The combustion is not reactor for this one. Then you should use the previous one to ensure the combustion is complete. And also note there is the maximum factor for the oxygen factor, that's 2.2. You cannot use that one higher than 2.2. Also for the oxygen dosing time, there's limit that is 99 seconds. So the oxygen dosing time is calculated based on the flow rate and the oxygen amount. So if, for example, if you have 200 milligram sample, you use the method B1.4. So the oxygen amount in the method is 200 milligram times 1.4. That is 280 milliliter oxygen. Then if you use method B, and then it will be divided 280 divided by 2, so that is 1.4 minutes. So this 1.4 minutes is the dosing time, and this dosing time should be less than 99 seconds. If it's longer, then we will get error message for the oxygen dosing timeout. So you should ensure you have the right amount sample to have the right amount of oxygen dosing. Otherwise, we may get some error message. And here are some other ways you can optimize the method for the new sample types. And this is a way you can observe the peak for the combustion. And if you have small tail following the nitrogen peak, that means oxygen is not enough. And this is very similar to you check the bypass. As mentioned in the previous method, and after you run example, if you run a bypass, if the bypass value here is very high, like this one is over 100, around 660, then you mean you have some carryover. That means the bypass the combustion is not reactor. You should increase the oxygen amount, or you have some peak tail for the nitrogen after nitrogen. So this is the way how you can optimize method. This is another very different from the first one. The first one is more usually for the new samples. You can run a series just to check which method is better. And here you just compare the bypass or just to check tail. It's quick way. You just tell if the bypass, if the combustion is complete. Then we just go to the next part. It's about calibration. So this is the way how you can create a calibration. So the first way is you estimate the sample weight and before the analysis according to the nitrogen content. Then you can run the samples with examples calibration to check if the nitrogen peak areas of the sample. And you will get the nitrogen peak area, then you can start to create your own calibrations range. It usually starts from 0 to double of the nitrogen peak area you get in the second step. So it's like you always ensure the nitrogen you want to measure is always in the median of the middle of the calibration curve. So this is the way how you create the calibrations. First, run new samples with example calibration to check the nitrogen peak of the sample. So you can run like unknowns, then you can run bypass. This is just the way ensure you have the right combustion. Then with this ways, you can get to the nitrogen peak, which is the peak. You can see the peak from the result tab. Then based on this result tab, you should have the calibrations like a double size of this peak. And then you can estimate what is the nitrogen range based on the EDTA for all other standard chemicals you want to build up. And then you can start build your calibration. And usually we use standard chemical that is EDTA in the method. And you have to build up a calibration start from 0 to double size of the nitrogen peak. And if you have 2 operators for the Dumatec, and you can create the calibrations by taking turns of the operators, taking turns weighing at the same weight, around same standard weight. So here is one example. It's like you start with like if you weigh 10 milligrams, so you have 2 operators. They weigh around the same, around 10 milligram, and for this one they weigh around the same for the 15 milligram. This is like 3 operators in this calibration curve. So you can do better, you get better linear calibrations for different operators to minimize the operator has different way of handling the weighing procedures. And also for the calibrations curve, we provide different calibration materials, standard for the calibration. We have 2 different, normally we have different standard. And the normal one is EDTA, that is for the normal samples and all the high nitrogen content samples. Also, we suggest you can use TEM. This is the formula for TEM. It contains 11.56% nitrogen, but we do not directly use TEM. We just dilute the TEM to 0.2%, 0.5% TEM solutions. And this TEM solution can use to build the low nitrogen content calibration curve. And this is used for the low nitrogen content sample. For example, the milk or the wastewater samples. And it's important that you register the TEM as standard in the standard tab in the table in the software, because usually EDTA is default. All the data information is there, but the TEM information is missing. So you have to enter TEM information as shown in this table. If you have 2 TEM, this is standard pure chemicals. You have TEM to 0.2% TEM. So the nitrogen content 0.2, you have 0.5% TEM, that's the nitrogen content 0.5. Then you can start to create the TEM calibrations from 0 to 1.5 milligram nitrogen. And this is one example how you can create. So we have 2 types of TEM. This is 2%, 0.2% is 0.5%. So you start with 0.2% from like 30 milligram the TEM solution to 210 milligram TEM solution. That is about 0.4 milligram nitrogen. Then you start to 30 milligram 0.5 TEM solution to 300 0.5. That is 1.5 milligram nitrogen. So you create a calibration curve for nitrogen from 0 to 1.5 milligram. So that the calibration is very suited for 0.75 milligram nitrogen. So this is very low absolute nitrogen, and you run it like usually for the wastewater samples. That means you can minimize sample weight in some way. And also there's another way you can just create a wider calibration curve. You can combine the TEM calibration with EDTA calibration. So for the lower end, you just have TEM solutions to create like from 0 to 0.6 milligram. Then you use EDTA for the calibration. Just have calibration from here to the larger range over to 11.6 milligram nitrogen. So you can have 2 range of calibration in the same calibration curve. One is from 0.0 to 0.6, the other is from 0.6 to 11.6. So it can be, this calibration can be used for either low nitrogen content or high. So it's more versatile calibration curve. And after you finish the calibration curve, it's also very important you verify the calibration curve. And this is normal way you verify the calibration curve. First, let's start with bypass. You have to run 6 bypass because in the system we have 6 CO2 trap. You have to stabilize all 6 CO2 traps. So that's why you run 6 bypass. Then you start to run the verification. So verification is like you choose a standard chemicals EDTA and choose a sample type is to verify and answer weight and run the calibration. So verify the sample to check the calibration curve. it's recommended to use the same batch standard chemical as verified sample to check the calibration curve. This is to prevent difference among the batches. And also you can use other standard chemical to verify the calibration curve. For example, this EDTA disodium salt. But in that case, we don't recommend you use the standard chemical in the sample table, but you run it as unknown. Then you can compare the result of the nitrogen content you get from the system and compare it with the theoretical nitrogen value. And usually we say the system should have a recovery between 90.5 to 100.5%. And when you have the verification test fails, here's a few tips what you can do to just figure out the problem. So always please make sure there's no leakage before you run the system, before you run the verification. If there's a leakage, it will get low result or unstable result. And then you also need to check the lifetime of the consumables and just ensure all the lifetime of the consumable, they are in the range, there's no issues for the consumable. And if you see the fields, if you run like 3 verification before you run sample, you have to run 6 to 12 verified samples to check the repeatability. And acceptable repeatability should be like plus minus 0.05% for the nitrogen. If you have good repeatability, but it's outside limits, then you can adjust the calibration curve. And that will be easier way. You just adjust it just to ensure your verification is in the range, because right now you have repeatable calibration. Or you can just create a new calibration, but it takes longer time. But if you have bad repeatability, that means you should create a new calibration. Or you have to check it hardware. You check consumables or check some consumables or check just some caliber the parts if there are any leakage or the consumable expires, the lifetime is end. So there's some other ways you should check if the repeatability is really bad. And here's some information about the calibration adjustment. As mentioned, if you have good repeatability, then you can just adjust the calibration in 2 ways. Here are the 2 methods you can do the calibration, the curve adjustment. And here's some information when you have to do the calibration adjustment. After changing consumables or the gas, it's recommended to run the verification sample to check the calibration curve. If the calibration result are out limits but with good repeatability, you can run adjust the calibration curve with at least 3 to 6 points. And this is for different CO2 traps and need to cover the whole range. So you can add a few points for all the CO2 traps to cover the range. And there are 2 ways. The first way is just you run the adjust samples. I will just show you how to run it in the next slide. And also you can run and add the points from the result tab. So first way is you just run the adjust samples. So this is the way how you do the adjust samples. You create you run the bypass, then you create the adjust sample type. For next sample, you enter the weight and you choose a standard. And then you select the calibration curve, which one you want to adjust. Then you start to run the analysis. And when you finish the run analysis, when the result there, this result will be automatically adjusted to added into the calibration curve. And then this calibration curve can be somehow adjusted. And the second way you want to do the adjustment is just you run the EDTA and with unknown sample, then you will get, for example, if you run 50 milligram, then you will get the value. And this is in the result tab, you get the value and you choose the result and right click, and then you have this adjust calibration. Because you run this with a certain calibration, so this result will be added for adjusting the calibration. This is an easier way. So we usually recommend you use this way to adjust the calibration. And also you may see some problem when you do the test. You will get unexpected results. Sometimes you will get high results, sometimes you will get low result. So if you get high result in system, so first you check the performance of calibration with standard chemicals, EDTA. And if it's not good for the calibration, for the verification, then you need to adjust the calibration. And secondly, you have to check the lifetime of the consumables, especially the combustion reactor and the reduction reactor. If the reactor have run out the lifetime, then the result usually it's higher. It's 30% higher than expectation. And also, if you get high result, then probably there's incomplete combustion. That means you should optimize method for the combustion, and more, for example, you should add more oxygen or just slow the combustion procedures to ensure the combustion is complete. And if you get a low result, that means probably you get a leakage in the system, then you should run a leak test to ensure there's no leakage in the system. And also check the calibration curve. If the calibration curve is like it's not the verification gets a low result, that means you have to adjust calibration curve somehow to ensure that your result can be accurate with the calibration curve. And also in the system, you will get some abnormal result. And the first picture here is just to show this normal peak. This is very sharp peak with the normal distribution. But sometimes when you get a peak like this, that means the analysis is not finished in 6 minutes. So because in the software there's normal setting, 6 minutes the analysis should be done. But of course you can adjust this analysis time, make it longer. But if you see this analysis is not done in 6 minutes, in most cases it's because the sample is not easy for burning, and the oxygen is not easy, it's not enough for burning. So that's you should slow the oxygen dosing rate and increase oxygen factor to ensure the complete combustion for the samples. And also you may see like this multiple peaks for the system when you do the analysis. You will see the first peak, like small peak, this is moisture, then you have the nitrogen peak, and then you have wider peak for the CO2. So you have to handle the issues step by step. First is remove the water, so that you should ensure all the water traps is working properly. Especially you should check the water traps free if it's working. So it's like you have to check the color for the silicon gel, just to ensure the silicon gel is yellow and there's no moisture inside. And also if you have the CO2 peak, then you should remove the gas in the CO2 trap to ensure the CO2 trap is working properly, can trap all the CO2 generated from procedures. Of course, there is an upper limit for the CO2 trap, and usually it's 104 milligram carbon in the sample. If the carbon content for the absolute carbon content, for example, is over 104 milligram in the sample for the carbon, then the CO2 trap, each CO2 trap cannot handle all the CO2 generated in the combustion. So then you will see some CO2 trap in the procedure. So always check if you have the right amount of the carbon. Otherwise, the excessive carbon can cause problem in the combustion procedures. And also the other thing, you will see the peak like this, like there's like the CO2 trap is somehow combined with the CO2, actually, sorry, this is not CO2 trap. Actually, we'll see a peak like this, and it can be the peak for this for the moisture is combined with nitrogen, or the nitrogen peak is combined with CO2. So you should check the CO2 trap, the lifetime. You have to do the degassing. As also I mentioned. Because you have a small CO2 trap, that usually means the CO2 is not complete absorber. You should check CO2 trap lifetime. So this is all the information here I want to share with you, and thank you for joining this session. Later, I will have here, I will just handle this to Bradley Bookman. He is a field service manager in North American. He will talk about some service information in North American. Thank you. Thank you for listening.
Hello, my name is Brad Buckman. I am the Field Service Manager for FOSS North America. I'll be going over our service structure, best way to reach service, field service engineer locations, and additional contact information. So our location, our FOSS North America headquarters is located in Eden Prairie, Minnesota. So This is our main headquarters in North America. This is where our call center, which is called OPE, One Point of Entry, resides. All of our offices, training rooms, we offer about 20 classes per year to our customers for FOSS instrumentation training. This is where our parts warehouse is. We have a repair shop for in-house repairs and QCs on new equipment. We also have an innovation lab where we have instruments on display for customer visits and demos. So our service team structure, we have 5 call center personnel, OPE. We also have 5 application specialists who do a lot of remote work on connectivity, calibrations, software upgrades, configurations, just to name a few. We also have 1 technical support person who is an extension of field service, and OPE who does just remote technical support. And we also have 30 field service engineers in the field. So what's the best way to reach service? The best way is again to call our FOSS call center, which is called OPE, One Point of Entry, 952-974-9892, option 3 for service, or you can email support team at fossna.com. This is where you can start a service request. You can order parts or reagents. You can ask for a salesperson. It's basically just one call for anything you need from FOSS. So here's a quick map showing locations of field service team in the US and Canada. We have a quite a knowledgeable group that range from experience on FOSS instrumentation anywhere from 5 years to 25 plus years. And if there's any other issues that are kind of outside the box, not normal service, anything you would need to talk to me about, any kind of an escalation, an ongoing issue, anything like that, feel free to reach me through our call center, or you can email me at buckman@fossna.com. So now I'm going to turn it back over to Marcy for her sales introductions. Thanks.
Thanks, Brad. Hi, I am the Industry Sales Manager at FOSS North America for the laboratory segment. In addition to that, I support all segments with our chemical analysis products. That would include the Keltec, SoxTech, FiberTech, Dumatec, as well as sample mills. If you have any questions about these products, you can reach me directly on my cell phone at 612-840-7522 or via email at mrussell@fossna.com. Otherwise, you are free to call our office at 952-974-9892. Extension 2 will bring you to our inside sales group. Thank you, and we can move on to the Q&A section now. Thanks.